Sean, I presume? Excellent. What are you talking about today?
I'm talking about tag-based policies for compartmentalization in C. And so I'm going to start out by briefly introducing the hardware tag monitoring system that our policies are enforced by and how we connect that to C. And then to our notion of compartmentalization as memory model. And I'm going to go through three distinct policies that explore this idea, and then briefly discuss the properties that they correspond to and our status in the work. And this is very much ongoing work. All right, so for starters, the hardware architecture is called PIPE, Programmable Interlocks for Policy Execution. And that is a hardware extension that attaches large metadata tags to all of the registers and memory on the chip. And at each execution cycle, the tags are updated, or the tag system issues a fail-stop if the tags represent a violation of some kind of policy. Policies are defined in software, so we have a lot of flexibility in what exactly tags mean and what kinds of behaviors are fail-stopped. But they are accelerated using a hardware cache, and so a lot of the concerns that we have for performance relate to what kinds of policies we can efficiently cache. And as for why you would bother messing around with all of this hardware when you could just write your code to be more secure, we generally assume that the target is for some large legacy code bases, of which there are many, and which have many security issues. So our goal is that our policies should be things that we can implement without having to manually rewrite or even necessarily annotate a lot of code by hand. A little bit's okay, but in general we want policies that already correspond to some established notion of security, or that fall out from some property of the language that isn't actually being enforced, as we see in C. And again, the main trade-off is that large tags give us the power to you have very expressive policies, that are very fine-grained, or use multiple policies at once, but that comes with a cost in terms of the performance of the cache. Pipe has already been used to implement a number of policies. Most of them target machine-level code. For example, information flow control and heap safety policies are aimed at just a generic machine-level program without any assumption about where it came from. Other policies take in some input from the compiler, like there's a stack-based a stack protection policy that needs to know where the stack is because it comes from the compiler. There is already some work in compartmentalization that uses a machine that's a little bit higher level and doesn't correspond to machine code. And ours is in that vein. We're attaching tag-based policies directly to our C semantics. And so this notion that we have a rule every cycle generalizes to a concept we call control points, where a general sense of places in the code that we need input as far as how to update tags. And we'll see one of those in a little bit. And now the compiler is completely in our trusted computing base, and we just assume that we can compile, and there is work to verify that. So since we have these very flexible policies, one advantage that we can give a hypothetical security engineer who's working with these is the ability to tune the level of safety that the policies are implementing. This could be for performance reasons. If we will have very secure policies that use a lot of tags, perhaps we want to turn the dial a little bit and find a policy that doesn't use quite so many tags. But it's also an issue because if we have these large legacy code bases, they often contain idioms that we might euphemistically call risky. Things that don't correspond to the C standard but we've gotten away with, and perhaps we'd like to keep getting away with them and not have programs that used to work suddenly. So on the far left of our dial, we have our underlying C variant, which we call concrete C, and it protects very little and just provides a concrete semantics for C, that then, if we turn the dial to the right with the tag policy, we move into the territory of tag C, which somehow refines the behavior of concrete C and makes it more, and adds a safety property. So concrete C is extremely permissive. We treat everything as an integer and define all memory behavior in terms of a flat memory model. The only thing that is protected, or the main thing that is protected, is control flow integrity and the necessary parts of the program of memory that's necessary to ensure that we can continue to protect it after compilation. And that's protected after compilation by a very simple tag policy, and then in tag C, when we have some high-level tag policy applied at the C level, that would also compile down and run in parallel with the basic policy that protects concrete C's assumptions. So now we're going to talk, so first I have to go through what a compartment is. We model compartments as collections of functions and variables, and possibly, depending on the exact memory model that we're using, they may own heap objects, or heap objects may be in some way outside of them or shareable. And they communicate through call and return interfaces, and that's the way that control gets passed between them. I'm only going to talk about policies in terms of how we enforce these the permissive versions of this structure, and not about mandatory access control. Saying that some function isn't able to be called from outside of a compartment, for instance, but that is completely doable in the tag-based setting. So as we go through the policies, first I'm going to have a very basic policy that doesn't permit any sharing and isolates everything. Then introducing sharing by a policy that allows, that treats everything as a capability. And then the sort of interesting middle point on the dial is what we call a pooled capability policy that essentially treats some things as fine-grained capabilities and others as coarser. And in this presentation, I'm going to emphasize, I'm only going to talk about the control points that correspond to pointer operations, because these policies are really only differentiated in their treatment of heap objects. And so these are the control points that demonstrate that. And then for each policy, I'll describe an associated memory model that we can use to reason about it. So the no sharing policy, first of all, this will be our first example of this visual metaphor. This is sort of a representation of a semantic step. So on the left, we have the malloc call, and on the right we have a representation of the pointer and some updated memory that corresponds to how state has changed as a result of the call. And these circles are a special tag called a PC tag. In principle corresponds to the tag on the program counter, but up at this level it's really just a generic context tag that's always accessible for any control point. And so we need to figure out what tags are going to be on various things. The small boxes attached to big boxes represent tags on values, and these second small boxes here indicate that these are memory locations, and the memory location themselves have tags associated with them that is separate from the tag on the value in the memory location. So in order to know how to color, how to fill in these tags, we go to our control point, which is associated with the semantic rule. And in this policy, the PC tag represents the active compartment, and so malloc t has to give us new tags based on the current active compartment, and the value tag doesn't actually mean anything in this policy. And what it will give us in this case is we keep the PC tag the same, and this tag in memory, this tag that will go to the memory addresses will correspond to that compartment. And then see the value tags don't mean anything, so when we are going to add any two numbers together, we just get a blank tag that says, oh, it's an integer, whatever, and keep the PC tag the same. And when the time comes to actually, say, store a value into memory, we're going to require that the PC tag and the memory address that's being stored into correspond to the same compartment. And if they do, that's fine, they stay the same. If they don't, say this is an unallocated address or it's allocated by another compartment, then this will issue a fail stop. So this, in principle, aligns with a memory model in which we're just strictly isolating the memory inside a compartment. So each compartment gets a large block within which it allocates locally. So it does still have to respect whether or not a particular address has been allocated. But within that block, it's free to forge pointers, do whatever kind of weird pointer arithmetic it wants, mess with the bits, and that will still be permitted. But the downside to this model, of course, is there's no way to share memory between objects, or between compartments. So we can't pass objects, we can only pass individual values, and this is very inefficient. So the other end of the dial is essentially a mode of sharing that represents permissible sharing by the possession of a valid pointer. We frequently call this a capability, as long as it's unforgeable. And by default, we assume that any valid pointer that is in some way obtained by a compartment was intentionally shared with that compartment, and so everything is fine. And this corresponds to the classic Comsort block offset model of memory, and so also the one that is supported by the C standard. And the only downside that we're going to, well, maybe not the only downside, but a downside of this is that we use a lot of tags. And so, as we see here with the malloc rule, whenever we allocate a new object, we are grabbing some fresh tag and tagging both the pointer and the memory of the object with it. So if we have a lot of allocations, we're generating a lot of fresh tags. Then as we do pointer arithmetic, in this case, the white boxes, again, are these sort of blank tags that mean, well, it's just an integer. So if we add an integer to a pointer, we get a pointer into the same block. And if we add two pointers together, that's not well defined, so that would be a fail stop. And then when the time comes to actually do a store, we again require that the pointer, in this case we require that the pointer value match the memory address, and it doesn't matter what the compartment is. But if the pointer tag is blank, and so the pointer is just an integer, that corresponds to having forged a pointer, and we don't allow that. And we also don't allow a mismatch between the pointer and memory tags. Very much emphasized that this policy uses a lot of tags. So the inspiration for the pooled capability model is just, let's try to use less tags. And so the intuition is any objects that aren't going to be shared, let's just put them all in one memory space again, and only use the fine-grained block offset model for things that might get shared. So this uses less tags, and it also has the effect of permitting some of these risky programming idioms that may well exist in our legacy code base, and just isolating them within a compartment. So on some level, it's just a combination of the two memory models. In this case, I'm going to omit the add rule because it's following that same sense of pointer arithmetic. And now we do distinguish between whether an allocation is marked to be shared versus being local. So if it's shared, it works just the same. And if it's local, now we create a capability that is tied to the current compartment. And once again, if we have a shareable object, we use the basic capability rule. But if the object, or if the tag corresponds to some compartment, then we require that that be the compartment that's currently executing. So in the event that we're wrong about an object being local and it gets out somehow, that's this example, even though it might, its pointer tag might match the memory tag, it doesn't match the current compartment, and this will be a fail stop. And whether or not this is something we actually need to worry about depends on exactly how we're determining which objects are local. And there are some different approaches. For one thing, we might use some form of static analysis to get a conservative estimate of just those objects we can guarantee won't leave the compartment. And if we do that, then there are some advantages to that. For one thing, it's something we can do automatically. And as long as we're conservative and we really are certain that things don't leave, then we're never going to cause a fail stop of that last type, where we shared something and it was a valid share according to the block offset model, but because we designated that object as local, we shouldn't have shared it. That will never happen as long as we're conservative. On the other hand, if we're conservative, then we're kind of giving up a lot of the advantage of reducing tags and also potentially marking things shareable that we would have liked to do some risky things to, some risky operations to. So on the other hand, if we manually look at the code and identify objects that we are confident won't escape, that can be slightly better. That can be slightly better in that regard, but on the other hand, we can no longer say that we're only going to err in one direction. So to validate these policies, we represent the associated memory models via a variant semantics that bakes the memory model in. And then our property for each one is that for any memory error in the memory model, we will also see a fail stop in tag C run with the appropriate policy. And we could think about whether we want to go the other way and say for any fail stop there is a corresponding error in the memory model, and that is doable for, if that's doable for the pool model. And so the current status of the work is that we're doing, I'm doing pencil and paper proofs, and they're not fully done, but I'm fairly confident with them, particularly the first two. So in conclusion, I've introduced a flexible enforcement mechanism for attaching tags at the C level, and some compartmentalization policies, of which the pooled capability one is the most interesting. In the future, we would also like to define some kind of broader property about substitutability, a notion that is general in compartmentalization, regardless of what memory model we're talking about, that we can capture similar behavior and substitute compartments if they have the same behavior. And also I'd like to find a way to extend the model to reason about confused deputies, which is an important concept that our model doesn't quite talk about. And my colleague Chris, who isn't here sadly, is working on a verified compiler for that concrete C and tagged C to machine code with machine level policy. And of course, it's also interesting to consider with these designs. They've been informed by the tag-based system, but there are other compartmentalization backends that they might also be suitable for. Certainly, Cherry loves the capability, and it's interesting. I'm not quite sure the degree to which the pooled model is actually that interesting in Cherry because it doesn't have the same performance requirements. And then of course there's the classic SFI and fewer bit tag architectures like ARM MTE might benefit from the pooled model. So now I'll take questions.
Were there any questions?
So you said that in earlier slide, function pointers are protected and some other things are protected. Protected means reading and writing to that location is failure, or
Yeah, so
that has a address, physical address, and then try to access that location with this forged address is.
yeah. So in the formal model, things like the control stack are actually just implicit in the model, and then and don't have addresses, and so that's justified by when we compile it, there will be a tag policy that will protect those addresses. Yeah.
One last question, please.
So it's more of a comment. So regarding your said about Cherry and having performance requirements. So your hybrid model reminds me of something that the Cherry people sometimes do, typically in pointer-heavy applications, where for some pointer-heavy sort of components, they choose to use integers or indexes into a large pointer instead of working with capabilities directly. For example, I think in some capability defined JavaScript virtual machine or something, and created something that went from it. So
Okay.
maybe you should.
Yeah, and yeah, there's that. There's two goals to the pool model. One is the performance, and the other is just allowing these more concrete GitHub behaviors on pointers. And so I can definitely see where you're talking to that shares as well.
Yeah, and Cherry's more, I think it's more about like the user is 64-bit versus capability is 128, so it's a lot of pointers that makes a difference.
Right. Okay, thanks. And I saw your hand.
I'm afraid we have to move on, but you're more than welcome to